Okay, thank you.
So here the atomic number 6 and here the proton number 13 because we have one more neutral number, correct?
So you guys have to be find out like that. Thank you. If you saw like that, just let me know. We know now the notation. Isotope of carbon summary. The atomic mass of carbon is here, and we now know. So what isotope does this belong to? So the atomic mass of carbon is 12, this one is this, and these two are isotope. Mass of carbon isotope. This is just because of change of neutron number. The atomic mass that is reported on the periodic table does not match any of the isotope mass number for carbon. Because this is not the regular, correct? This is the isotopic, and periodic table show the regular their properties and regular elemental mass and atomic number. Sorry for that. Just it shows its own. Element carbon is composed of all the isotopes in a fixed composition. So here the abundance of formula mass for the C12, C13 and C14. Isotope calculations. The mass number reported on the periodic table is a weighted average mass of the three different carbon isotopes. So atomic mass, in that case, this is the weighted average mass. In case of C12, in case of C13, and in case of C14. So that's why the average atomic mass is like that, this abundance. And C14 actually, when we go for the calculation, we find the negligible abundance. So if we have some details, I will show you. What is the average atomic mass of an element that consists of 62.6% of isotope with a mass of 186.9 U and 37.4% of isotope with a mass of 184.9 U? Let's see the measurement. So the percent abundance, what is the percent means? Percent means part per 100, correct? So when we are talking about 62.6% abundance, that means this one. And we already have the mass with that. So we have to be do like that. And also plus we have another 37.4. So 184 for second one comes from here. And then we will be doing 37.4 per 100. So what we will do, we will find. So this is our rules. So we have to be make it average for this one and for this one. And we already have for this one, we have here. So this is the total and this is the 62.6% of 100. So this is how we have to measure it. So remember the percent means part per 100. So in that case, we have to, no, we don't have to find for the 100%. We have to find for 62.6. Now, if I ask you, not 60, not 62, if I ask you that 84%, so how you will do? You will just change here, correct? Sorry, here it will be changed. So 84 divided by 100. So this is how you have to do these math calculations. Naturally occurring, actually, this type of question I should not show here because, but it's okay. Let's, you will have a easy to know the what type of format is going to be for exam. So naturally occurring chlorine consists of two isotopes, and like Cl35 and Cl37. This is for the chlorine. So that means here the 2 neutron number is higher than the regular one. Their relative abundance are 75.78 and 24.22. So how do the number of proton, neutron, and electron for the atoms of these isotopes compare? So we know how to do the average, and also we know the percent abundance. So if we now look into here, so each atom has the same number of proton and the same number of neutron, but a different number of electron. No, this is not the correct. Correct will be the number C. Each atom has the same number of protons, same number of electrons, but a different number of neutrons. See here, 35 and 37. This is just a typo mistake, okay? So for the correct answer will be the C. Not typo, it just formatting comes little down. So the correct answer must be C. Now, the atoms are made, as we know, the atoms made up of parts proton, neutron, and electron. We model the electronic cloud using the atomic orbital. Atomic orbital come in four relatively well characterized shapes: S, P, D, and F. As I said, that when atoms normally the outside of the nucleus and they continuously move, but with a different energy level. And that's why, according to the energy level and movement pattern, we have four different types of orbital. So S, P, D, and F. The different atomic orbitals have different properties like shape and energy, as I just said. So we have some calculations like, the first shell, and we say this is subshell. So first shell, 1s, if we consider 1s, 2s, 3s, s orbital are spherically shaped, and the innermost orbital is the smallest. So s is most smallest, and then it's spreading, its size and shape is getting larger. Here, and also we know, I'm not sure, but maybe you study the, when the atom, some elements can give the electron and some elements can take the electron, correct? Normally metals give the electrons, that's why they are cation and positive charge, correct? So in that case, do you guys know that we have some rules called the electronic configuration based on the orbitals? The first shell can be maximum 2 electrons, second shell maximum 8 electrons, third shell can be maximum 18 electrons. So if we know the number of maximum electron can be reside on different subshell, then we can easily prove that which element will be give the electron or which element will be take the electron. The reason we have the another octet rule in case of orbital theory, because that every element want to be stable. And if they want to be stable, their last final shell should be the 8 electron. So when we draw this electronic configuration, show here. see here. Oh, it's not coming. Okay, go back. Okay, just see this one. I need a little bit of bigger picture. Okay, let's see. So now we are talking about the cell, the S, P, D. So there also we talk the subshell like that. So in case of sodium, so the sodium is 11, correct? So 281, see this one. And even in case of chlorine is 17, so 286. So what happened? Sodium is a metal and cation sodium can give the electron. How? The reason is here. Because if sodium can give away this extra electron, sodium's final shell contains the 8 electron and get stable. In case of chlorine have one electron deficient. So chlorine take this extra electron from sodium and make this outer shell 8 and stable. This is how actually the chemical bond that we are going to talk in our next lecture also, the atoms. And this actually comes from our orbital thing. So let's go move on. So here the orbitals get bigger as you move further away from the nucleus. And as I said that it actually looks like the onion, like that. If we cut the onion in the center or middle, like that. Like that. So if we have some onion like that, and if we cut, the way we look into similar way, here we look. And as I said that the first shell, we have maximum 2 electrons. See, each s orbital holds maximum 2 electrons. Now go back to p orbitals shape like dumbbell shape, and there are 3 types of p orbitals. And p orbital holds maximum 2 electrons. So 6 total. Since this is the 3 types, so that's why s orbital 2 and p orbital 6 total 8 electrons in the second shell. Now we have the d orbital. This d orbital called the clover shaped, this type of shape, and they are the 5 types of d orbital, and each d orbital holds maximum 2, so the 10 electrons. So 10 plus, the first and second was 8, so 10 plus 8 is 18. So that's we say that PD, third shell, can have maximum 18 electrons. D orbital are little bit of complicated. There are 5 types of, as we see. And for this course, you need to be know that only this shape. And if you have, I will also show you that how to draw. I already showed the sodium chloride. If I get the chance, I will show some more. So the periodic table indicates the orbitals. So from the periodic table, we can guess the s orbital, the first shell 2, and d orbital is here, and p orbital is here. And if you go back the maximum number of electron, you will able to match it. And how it happens, actually the way I show here, this is how we can draw. Okay, that time it will be matching. The period indicates the orbital number this way, and energy level. The group indicates the shape. The periodic table indicates the orbital. See, we can use the periodic table to find the orbitals of any element. So in that case, we could look into here. Let's look at our friend oxygen. 1s, 2s, 2p. So now, here we have some color. Let's go here. Atomic orbitals have different energy. So this is how. This is how they draw oxygen 1s2, 2s2, 2p4. So how it comes? Let's first see the oxygen is 8. Okay. So oxygen's proton number is 8, atomic number, correct? So what happened is, first shell, this one, maximum 2. So that's why this is 2. We draw like that. And second, S plus P, 6. So 2S and 2, we have remaining 4. So we can draw like that, 2S and the 4. So that is the oxygen, the final shell, and this is called the valency shell. Okay? So oxygen have 2 electron less. That's why oxygen's valency is 2 and it is negative, because oxygen needs to take 2 electrons from some other elements. So this is how actually, but for me personally, I believe that if you just know the how many electrons can reside in s, p and d orbital, you can draw very easily like that. But however, as we know here, the 1s maximum 2, then 2p, if you sit like that 1 2, then you will again able to find it. Electron configuration of oxygen. See, this is the 1s, maximum 2 electron. Here the 2s2, this is the 2s2, one room, and here 2p4, 1 2 3 4. So this is how we can draw it, but I will suggest you, if you do this way, it makes more easier. But anyway, we need to have this example so we can see it like that. Electronic configuration of oxide. What about the O2 minus? O2 minus has gained 2 electrons. So when it gained 2 electrons, as I said, every atom wants to be stable in the final shell, and stability, if you want to get the stability, you have to have 8 electrons. And this is the reason that oxygen needs to gain 2 electrons from some other things. So when oxygen gain, you can see the difference here, 1 2 3, and there was, but when it gain, these two they gain. Got it? So total 1 2 3 4 5 6 7, not these two. So these two gain, and this 4 6, and here we have the 2. So total 8. So the electrons go into the next available energy level. So that's why it go to the right. Electron configuration of sodium. 1s2 here, 2s2 here, 2p6, 1 2 3 4 5 6, and we have extra one. You know, we show you the here, the sodium, the extra one. See the extra one? This extra one is here. We go. This one. So this one, sodium don't need it. So what sodium do? Sodium donate this one. When sodium donate it, sodium get the positive sodium cation. See here? And this donation taken by other anion. The electron comes out of the highest energy orbital. Sodium is also isoelectronic with neon. So when we do like that, they got the same amount of the neon in the periodic table. So now it can be little complicated. I need to go back to the periodic table. I will show you the neon, that it will be easy for you. See, neon. Yeah, neon 10. See? Neon 10. Let's move on. Okay. So normally sodium was 11. So when sodium gives away the 1 electron and get 10, that find the neon 10. So let's look into neon. Do we have, can you find out the neon 10? Neon. Which way the neon? There, here we go. Got it? This is the neon. So when sodium gives out 1 electron, then it has the 10 and that equivalent to neon. That's they are telling in your lecture. That's sodium, not sodium, sodium ion. Okay? Sodium ion is isoelectronic with neon. Here the similar way we have to go. So 1s2, 2s2 and 2p6. And also we have 3p, 4s, 3d. That's why it comes here. And here we go. Now, here the correct electronic configuration for the iron ion is. Which one is the correct configuration of iron? As I said, that you need to learn this way. So let's find out first iron atomic or electron number. Iron how many? Fe. Find the Fe. Then you will easy to find it. Iron. Where the iron? Can you find it?
26.
Which?
26. In the middle. Atomic number 26. In the middle.
In the middle, correct? First row? No. Second. Fe. Okay, I'm going. Here we go. Thank you. Yeah. So iron we have 26, correct? And they tricks you argon, air. Find now argon, air. The question tricks you, so that's why I'm looking. Argon, air, correct? Here we go. Yeah, 18, correct? So what they did, what they ask you, they didn't give you here 18 till. They show you here argon because argon already have a 18 electron. Got it? So now you have to find out, count the electron number here, 4s and d level, and then you have to find out which one is the correct configuration for the iron 3 plus. That means let's again go back to the electronic configuration of iron. It's interesting. Iron 3 plus. This one. See, this is okay. 2, then what we saw? How many we saw the number? 26. Yes. So 2, 8, 10, 10, and here must 18. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so in some cases, what happened? Some cases, theoretically, it looks that we have to be masked 18, but sometimes energy level difference and electron can be jump out to other orbital. That's why they show here the, here we go, the S and, SPD and also the 4S. So now 26 and argon have 18. So 18 plus 2, 20. 20 plus 3 is 23. And here 18 plus 5, 18 plus 5 is 23. But the correct answer is telling C, because of the energy differences, they jump here. So we don't have the 4s level to go. This is the another level. So since iron donate the 3 electron, see there the question was 3 plus. 3 plus means iron already the ferrous and ferric, correct? So there the number is not same. The number is different because iron can donate. And here ferrous and ferric, one is 2 electron and ferrous 2 and ferric is 3. So that's why here this is the correct answer. Let's see the explanation. Iron has lost 3 electrons here. That's why we always know that when we donate the electron, we got the cation and lost 3 electrons. So the electrons will come out the 4s orbital before they come out the 3d orbital. 3d is lower in energy. So that's I was telling that we have the rules, but due to the energy level difference, sometimes it happens in that case here because both are 23, but not the correct answer is this because they first lose from here because of the energy level and 3D level is lower energy. So that's why higher energy level lost first than the lower energy level, and that's why this is the correct answer, and this is the exception one, so please be remember. But I will suggest you when you will practice, you guys can do little bit of you can just manually do that. First step 2, second 8, third 18, and fourth 32. But in some exception that we sometimes mention in the that are not so much, that are very fewer. Now magnetism and electron pairing. Electrons have a spin, act as if they are little magnet. When we fill orbital with electrons, we fill each orbital with unpaired electron first and then begin to pair them. When two electrons are in the same orbital subshell, they will spin up and spin down, and their magnetic moments cancel out, like positive negative. So one is up, one is down, and their moment is cancel out. If any two p of the electrons are unpaired, the atom is said to be paramagnetic. And if the like that unpaired, and when the electrons 2p electrons are paired like that, spin up and spin down, we say this is diamagnetic. And now we have some question level here, and that will be given the titanium atom has 22 electrons and electron configuration is this. What can we say about the titanium atom? Titanium atom is paramagnetic. It has unpaired electrons. So that means we have to first draw the electron, then we can find out. So drawing is like that. There are two d electrons and this will be unpaired. D4 and D9 exception. Okay, that's I need a little bit of talk. I need little bit of more explanation that I'm going to give you the next class, because if I don't say the why, it's going to be not complete. So this topic I will be little bit of discuss tomorrow, and then I will be move on to the topic 3. So today till now here we will